السادة الحضور الكرام، الضيوف الكرام، السلام عليكم ورحمة الله وبركاته. في البداية نود أن نرحب ونشكر لكم تشريفكم بحضوركم والمشاركة في الندوة التعريفية بآخر التطورات والأبحاث العلمية في مجال الخلطات الأسفلتية المحسنة السوبر ريف، الذي سيقوم البروفيسور جيفري ميشيل راو أحد أهم المتخصصين في هذا المجال بإلقاء الضوء عليها. والآن الكلمة للأستاذ فهد السهلي، رئيس مجموعة السهلي للمقاولات ووكيل شركة كوبر بالمملكة. فليتفضل.
بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على خاتم الأنبياء والمرسلين، وبعد. أيها الحضور الكريم، السلام عليكم ورحمة الله وبركاته. ومنذ خلق الله الإنسان لعبادته أولا،
ومن ثم إعمار الأرض وتهيئتها لتناسبه ويتمكن من العيش عليها، بدأ الخلق في الكد والعمل بجد واجتهاد لتطوير ورفع مستوى سبل العيش، وبدأت الدول تتنافس في تقنيات التطوير والتقدم في مختلف المجالات. ونحن في مجموعة السهل للتجارة والمقاولات نساهم على قدر ما أوتينا من طاقة، ونسخر كل إمكانياتنا ومواردنا البشرية والمادية لخدمة وطننا والمساهمة في إعمار الأرض وتطوير وتنفيذ المشاريع على ضوء أسس علمية وتقنيات عالية لنكون عضوا فعالا في ذلك، خاصة وأن حكومتنا الرشيدة شجعت وساندت أبناء وطنها، وعلى رأسهم خادم الحرمين الشريفين الملك عبد الله بن عبد العزيز آل سعود حفظه الله ورعاه. وقد دأبنا على الاستفادة من الخبرات العالمية، وعزمنا على أن نبدأ من حيث انتهى الآخرون، واضعين نصب أعيننا مستقبل مشرق بإذن الله بالتعاون مع نخبة من العلماء والمهندسين ذوي الخبرات العملية والعلمية العالية، والذي نعتز ونتشرف بطرحها بين أيديكم للاستفادة منها. ومن هذا المنطلق نقدم لكم مجموعة من الخبراء من شركة كوبر البريطانية الأمريكية للتكنولوجيا، وهم البروفيسور جيفري ميشيل المتخصص في مجال الأسفلت والسوبر بيف، والسيد بيتر جرافتون المدير التنفيذي لشركة كوبر البريطانية، والسيد أندرو كوبر مدير البحوث والتكنولوجيا، وذلك للاستفادة بشكل مباشر من خبراتهم وتجاربهم وما توصلوا إليه من تقنيات حديثة في مجال الفحص والتحليل للتربة والخرسانة والأسفلت بصورة عامة، ومعدات السوبر بيف بصورة خاصة. أيها الحضور الكريم، نتقدم إليكم نحن مجموعة السهلي بالشكر الجزيل لإتاحة هذه الفرصة لطرح هذا العمل المتواضع، والذي نرى فيه إثراء وتطويرا للخدمات المقدمة في هذا المجال. كما نرحب بآرائكم ومقترحاتكم، ولكم خالص شكرنا وتقديرنا، والسلام عليكم ورحمة الله وبركاته.
أما الآن فمع كلمة البروفيسور جيفري ميشيل راو أحد أهم المتخصصين في هذا المجال، فليتفضل.
Thank you very much. I'm just going to provide a little introduction. My first thing I'd like to say is thank you very much for inviting me here to the Kingdom of Saudi Arabia. It's a great pleasure for me to be here with my colleagues. So thank you very much for being here and joining us today. Thank you for our sponsors as well for inviting us here and being our technology partners. A little bit about myself. I have worked in asphalt materials for 38 years. I started work in asphalt materials in an asphalt plant, shaking sieves, working in a laboratory. Since that time I became more technical. I did degrees, did a PhD, worked on the Superpave program in the late 1980s, early 1990s, which is where I met my colleague, Mr. Andrew Cooper's father, Keith Cooper. We worked together at the University of Nottingham with Professor Steve Brown. And after that time, I went to the United States, and I lived in the United States since 1993, and I'm involved very much in the implementation of Superpave and the continuing development of Superpave. So I've been involved in Superpave for around about 26 years now of my working career. I worked on multiple projects, and I'll talk a little bit about that as we start. What I'd like to do in this presentation, I'm going to talk, and then I'm going to invite Andrew and Peter to talk as well, to give some information that will supplement some of the information I'm going to talk about. But in the first instance, what I'd like to do is invite Mr. Peter Grafton, the Managing Director of Cooper, to come and explain the background of the Cooper company to us.
Thank you, Jeff. Yeah, just to back up really what Jeff said there first in terms of a thank you for making us so welcome in the Kingdom of Saudi Arabia. Thank you for everyone at the Ministry for holding this conference today, and for Fahad at sahly for making such a good welcome to us all and making us feel comfortable in your fine country. I'm only going to be talking for 1 minute because there's lots of important things to talk about SuperPave. But yeah, as Jeff said, I'm Managing Director of Cooper Technology. I've been with Cooper for 8 years now. Cooper has been founded for around 25 years. Founder Keith Cooper, as Jeff said, came out of Nottingham University, where Keith invented the Nottingham asphalt tester. The Nottingham asphalt tester was the first piece of test equipment to test the dynamic performance properties of asphalt. Cooper now owns James Cox and Sons. James Cox and Sons, like Cooper, came from university background, University of Berkeley in California, where Jim Cox was working with a team of academics to develop equipment to find out more about the mechanical properties of asphalt. We as a group own a couple more businesses, which I'll talk about in the next couple of slides. And our core business, as we've said, is the design and development of asphalt testing equipment. We have a team of people over in the UK that cover all disciplines: software, electronics, hydraulics, pneumatics, mechanics, to put together a package that satisfies research and everyday testing needs. On the slide you can see some of the equipment that we make: a Texas overlay tester for fatigue, Hamburg wheel tracker for rutting and stripping, 4-point bending for fatigue. We've got sample compaction machines. We've got DSRs and RTFOs for bitumen, Violet for bitumen. We've got cracking test equipment, and we've got equipment that prepares test samples and enables you to have samples in any shape, to put them in equipment to be tested. Jeff. Right, one thing I'd like to say is calibration. Calibration and training, really. Calibration is fundamental and critical to ensure that the results that you see that the machines give as an output can be relied upon. We take the accuracy and repeatability of our machines seriously. And as such, our laboratory in the UK is that it is a fully accredited UCAS calibration laboratory. We've got the accreditation stamp from UCAS, and to my knowledge we're the only ones that have got that in our field. So if our machine gives an output, we're confident that we've got external accreditation that the outputs that our equipment gives are good. It's really important when you're buying capital equipment that you can rely on the results that you're given. I said earlier we own a couple of other companies. One of those companies is Merkel Engineering. We acquired Merkel Engineering a few years ago now. We're precision engineers. Our company's been growing rapidly. We've seen rapid growth this last 8 years, and ensuring we had continuation of machine parts was important to us, and we thought to ensure we get the quality that we need and parts delivered on time, we'll invest in an engineering company. So we own our own engineering company, and the parts for the machines are made in the UK by us. Another company that is ours is Test International. We've been dealing with customers for many, many years, and customers coming to us all the time and saying the same thing: we want more products. So we set up Test International, and Test International works to complement the Cooper range, supplying equipment into the soils testing and concrete testing arenas. So overall now, with our British and American companies, alongside Test International, I believe that we're well positioned to supply you with your every need. So, back to America, and Jeff will start now talking to you about the concept and the development of SuperPave. Thank you.
This slide for me is quite interesting. I'll just say about who these people are. During the SHARP program, I had the pleasure to work with Professor Carl Monosmith, and you can see him there on the left-hand side. That photograph was probably taken around about 1992 when he was working with Jim Cox. Jim Cox was he formed the company James Cox and Sons, and this is the company that was recently being acquired by Cooper. Cooper worked also on the SHARP program with the relationship with the University of Nottingham. Carl Monosmith worked with Jim Cox and Sons and their company when he was working with the University of Berkeley. We were both working on the same SHARP project leading into the SuperPave technology. On the bottom right there, you can see a more recent picture, a somewhat more aged Carl Monosmith in that picture, with myself on the left and Andrew on the right, when we visited with Carl in about 2 years ago in Sacramento. I believe that photograph was taken. So anyway, this just shows the linkage that we have between the American technology and the European technology. Both Andrew and I sit on European committees and USA specification committees. We're both involved in standard development in the two continents. So what was SuperPave? To define SuperPave, SuperPave was a research project conducted between 1987 and 1993. A strategic highway research program. The total amount of spend was $250 million, and of that, $50 million was spent on developing new ways to test and design asphalt materials. The final product of the asphalt program of the SHARP research effort was a product called SuperPave, and SuperPave is an acronym, and it stands for Superior Performing Asphalt Pavement. And it really represents an improved system of specifying asphalt materials, that being asphalt binders and asphalt mixtures. And it included some pavement performance prediction tools, but those pavement performance prediction tools at that stage were largely not implemented, and the pavement performance prediction is really being implemented under another project being conducted in the US. I have a couple of these slides. We'll make sure that you have copies of these slides through our partners here, so that there'll be some USB sticks, or we'll email them to you. So don't worry about necessarily having to write all this stuff down, but we'll make sure you get the copies of the slides at some stage. This shows the organization of the SuperPave project, or the SHARP project, funded by the National Research Council. Then had a executive director, a SHARP executive director, and then you had a program manager here, and underneath the program manager you had 5 contracts. You had a contract called A001, which was a management contract, and then you had underneath that contract a series of contractors. You had A002 was looking at binders and chemistry, A003 was looking at mixtures, A004 was looking at the asphalt modifiers, A005 was looking at the asphalt models. One of the things we had these things called loan staff. Loan staff was staff from other organizations which was linked to the SHARP program. So, for example, we had TRL in London, or in England, lend the SHARP program staff. We had Brian Cox from TRL. We had loan staff from Ireland. We had loan staff from the Netherlands. from Canada, from other countries. So while this program, people think of it as an American program, it's really an international program. We had a conference in London which dealt with the international aspects of SHARP and sharing the benefits. So I would say that the SHARP program is best viewed as a program that was developed that involved a lot of international cooperation to develop the ideas that went into the SuperPave system. There's various things that were developed. In terms of developing the binder products, this was the plan that occurred. You had the A002A and 2B contractors developing the test results and the test methods, and these were then validated by tests on modified binder, tests on conventional binders, and there was a validation system. And at the end of the day, the A001 contractor was responsible for developing the binder specifications and the contract. There was a similar thing with the mixture. There was a flow of information through the different contracts that were conducted. A003 was the lead contractor for mixtures. That was Professor Carl Monosmith. Professor Carl Monosmith is at the University of Berkeley in California, and he had a series of subcontractors. Oregon State University, Professor Gary Hicks. We also had people like Ted Vincent, various other folks. Ron Terrell was there, a good friend and colleague of mine. And then the University of Nottingham was another subcontractor. University of North Carolina, another subcontractor. We had a series of people working with Carl and his team over here, and then there was some validation and model development to the A005 team. This was with Bob Litton in the Texas A&M University, and then it was implemented by the A001 team, which was Tom Kennedy at the University of Texas. People like Tom Kennedy, Jim Moltrop, Ron Kaminsky were all involved in this implementation effort. Now, in terms of what's going on in the SuperPave specifications, we consider with the binder 3 different types of aging conditions. Consider the binder in the original condition, the unaged condition. Consider it after rolling thin film oven aging and pressure aging vessel aging. The idea with these different aging conditions is that this represents the binder in the original condition when it would be mixed with the aggregates and making your hot mix material. Also, in the original condition, we're more concerned about the rotting and deformation properties. Rolling thin film oven is still an early life condition, so we still evaluate rotting conditions for the rolling thin film oven aged binder. Pressure aging vessel is more of a long-term condition where we're concerned about performance such as cracking and how the material is going to perform after a longer period of time. So we condition the binder to these 3 conditions, and then we evaluate these different distress types. Single event cold temperature cracking. This is what a road will look like when it has cold temperature cracking. You get these discrete transverse cracks across the road. This picture of the road here is at Lamont, which is near Edmonton in Canada, and very cold climate, a lot colder than you have here, and you probably don't see cracking too much like that, even though in some desert climates you can get block cracking and you can get cracking associated with thermal events. So, though this is cold temperature, you still have to be very careful of cracking performance in desert climates where you get big diurnal swings in temperature. Fatigue cracking, this shows a picture of fatigue cracking, and then here we have rotting over here. The fatigue cracking is evaluated on the pressure aging vessel material. Rotting is looking at the original and the RTFOT material. So this picture here is showing close to a coal mine in Kentucky. This is going up a big hill, and you see you could nearly drive along this road with your eyes closed because the tires would just follow the ruts or the deformation in the road there. So, in terms of this specification, what was different with the SuperPave specification versus the earlier test, or the earlier specifications? First of all, in SuperPave, we have a very strong consideration of climate. The biggest difference with the SuperPave specifications is we have the same property adopted, but we test that property at different temperatures. If you go back to the pen specification, in the pen spec, we have maybe 50 pen, 70 pen, 100 pen, but we do the tests all at 25 degrees C. Well, you know, the road isn't at 25 degrees C, the road might be at 50 degrees C or 70 degrees C. So in one way it makes sense to test the property that you're concerned about at the environmental temperature of the road. So this is what we did in SuperPave, and this was a departure from our previous specifications, which were either velocity specifications or penetration specifications. In the SuperPave specifications, say the property of the binder must be this to resist deformation, or it must be this to have good fatigue performance. And then we evaluate that property at that environmental condition that the pavement is in. But always the same, whether it's in the north part of Canada or here in Saudi Arabia. It's still the same weight, you know, maybe 40, 50 tons at the most, maybe 20, 30 tons on an average sort of truck. So the truck still stays the same. The specification is based upon the rheology. The original idea in the research was to base it upon something called the rheological index. The rheological index is something like the penetration index or the penetration viscosity number. It gives some sort of indication of the temperature susceptibility of the binder. And I'll talk a little bit more about this later on. But the concept of the rheological index was felt too complicated for the average engineer. And so we made it more simple, and we used two results at the PAV condition. So by specifying two results in the PAV condition, we actually are controlling the rheological index. So what we did is we specified the bending beam rheometer stiffness, and we specified the stiffness with an 8 millimeter dynamic shear rheometer on the PAV binder, and it was a back way of introducing the rheological index to the specification without calling it the rheological index. So it was an easier way of getting it in. Dynamic shear rheometer was basically a piece of equipment that was already in existence at the time of SuperPave. It was refined, it was improved, and it was adopted for the intermediate and high temperatures. The bending beam rheometer was adopted for the low temperature due to the limitations you have with a DSR of testing those bitumens when they're very stiff. So a bending beam rheometer does a better job at evaluating the stiffness or the rheology of the asphalt binder at those low temperatures, or when the material is behaving in a stiff manner. The specifications that were produced are in the AASHTO M320, and you have a table where you have these different PG grades, and then what we have is a series of properties in these horizontal tables. So example, here you have a dynamic creep stiffness. This number here, I know you can't read it on the slide, but it says 1 kilopascal, and the material has to be 1 kilopascal. For this particular grade, 58 at 58 degrees C. This particular grade, it has to be 1 kilopascal at 64 degrees C, and so on. You basically are changing the temperature of the test rather than changing the property. And there's this section here deals with properties on the unaged binder, then you have properties on the RTFOT binder, and then you have properties on the PAV aged binder. So you have different properties to control the parts of the specification that deal with rutting, parts of the specification that deal with fatigue, and also with low temperature cracking. And then you have flash point included in the specification. There's a safety aspect. You have viscosity included, which makes sure that you can mix the material and pump the material in the asphalt plants. So there are these types of requirements as well. And then there's one or two additional requirements in the footnotes, things like solubility, etc., for the bitumen. In terms of the mixture specifications, I always recommend that folks get this Asphalt Institute publication. It's called SP2. It deals with the superpave mixture design procedure. It's a very nice publication. You can order it online. It's fairly inexpensive, and it deals with the volumetric specifications and the geometry compaction. We have consensus properties for aggregates. What we did in the superpave specification development, we had some expert task groups, sat these expert task groups together, and we made them decide on what aggregate properties they felt were appropriate. So we have aggregate properties for flat and elongated particles, for the strength of the particles, and in a way that wasn't too different from what we had in our specifications before. Very limited use of the mixed design performance tests. Had tests like the simple shear device. And some of these tests, when they were first developed in superpave, were very complicated. You had some very sophisticated pieces of equipment. The things that have been adopted in the specification since superpave, some folks are still using simple shear tests, but it's very limited, and really the research folks are using that. The indirect tensile test has been adopted in some procedures like the mechanistic empirical pavement design. There's some limited adoption of the bending beam fatigue test. There's probably about 6 or 7 US states that are using bending beam fatigue test for evaluating specialized mixes. There's some fairly limited adoption of the mix side of it, and we'll show you some of that a little bit later on. So what I want to talk about is some of the developments that have gone on since superpave was initially published, which was around about 94, 95, and what we're doing today. Talk about some of the newer ideas with testing. So since that time in the early 1990s, we've had a series of expert task groups. These expert task groups are very important for the implementation of the ideas that are being developed by the researchers and the academic folks, because they have a research group, have some industry folks like the contractors, and then you have government folks like the departments of transports, the guys specifying the asphalt mixes. And these are all working together. This implementation is done via federal highways and also involves some continuing research and development by task groups working for those expert task groups. So what we have done is this work has resulted in some changes, some alternate binder tests and better understanding of the binder properties, and I'll talk a little bit about these. On the mixes, we've made a bit more use of wheel tracking tests, like the Hamburg test. We're looking at different cracking tests, and I'm going to add a little bit of discussion how we should apply this to different climates. I know here in Saudi Arabia, you adopted some parts of the superpave system maybe about 8 years ago, I think, if I'm correct. 7, 8 years ago you started looking at superpave specification. But around about that time, we also changed in the US the way that we calculate the high PG grade. In the initial implementation of superpave, and if you go and get some of those early Asphalt Institute books that were published in the early part of the 1990s, you will see that they used something called the mean 7-day high average air temperature to determine the high PG grade for a particular region. We found in the US that didn't work. It didn't give us the right high temperature. So we changed it, and we now use a 3-day weighted high temperature to get the PG grade. But there's a different algorithm there. So if you set your PG grades based upon the first round of implementation that came out of SuperPave were PG grade based on a different system now what is being used in the US. So that's an important consideration. If you want any information on that, I can send you the references and I can send you the papers. Okay? So that's an important thing there. What we've done with Cooper is we've developed linkage in with all the key industry experts. I sit on expert task group for both binder and mixture. I'm a member of the binder expert task group. I lead some of the committee and some of the work in the mixture. Andrew is also involved. Peter is often in the States. So what we've done is we've linked in with all the key people to make sure that we can continually bring you the best possible support in what's going on and the changes in these specifications. So the newer ideas with testing, what do we see changing? What I should mention is, Andrew, do you want to come and just talk about what's going on with the test equipment here and just discuss particularly the DSR test equipment? Next. Okay. Well, these are the bits of test equipment that we have. Oops, sorry, how did that move? Okay. These are the bits of test equipment that we have coming in the SuperPave system for the binders. We have the rolling thin film oven, pressure aging vessel, the vacuum degassing oven. Here the idea of the vacuum degassing oven is particularly for things like direct tension tests down here. They're very sensitive to any air bubbles you have in the specimen. The vacuum degassing really makes sure you get rid of all those air bubbles. Rotational viscometer, the dynamic shear rheometer, bending beam rheometer, and direct tension test. Now as Cooper, we support all of this equipment, and what I'd like Andrew to do is just to take a minute and to talk about the support on some of the equipment.
Yeah, the main thing I wanted to point out on this slide and the next slide is here you see your classic Malvern dynamic shear rheometer. We've seen them downstairs in the laboratories, we see them all over the world. And there we have it in blue. Now this is something that Cooper has done recently, and this is a Malvern DSR, but if you see on the front there, it's marked Cooper. Now we've worked directly with Malvern to produce this dynamic shear rheometer, and the purpose of showing this slide is to demonstrate we're not just somebody that is going to resell equipment. The reason we're working with Malvern is that we want to offer great support. We want to put these devices into laboratories, but then to support them for the length of their life, not to sell and let them run into disrepair, but to maintain, to service, and to carry on using them and keeping them going for years and years to come. And this is one of the main things that we are doing here with sahly is going to work together to ensure that you get great support on these pieces of equipment.
The other thing I'll just add on the relationship with Malvern is, I've had a business relationship with Malvern now for about 16 years. They've been selling software as part of their technology package. So the fact that as a team of people here working with Malvern, or Bolin as it was back then, Bolin was the original company that Malvern acquired and incorporated into its business. So some people think of these rheometers as Bolin rheometers, depending on when you actually bought the equipment. But we've been working with that company now for 15 plus years. So we have a very good working relationship with all those folks. We've known them for a very long period of time. But that is something that we would be very happy to support, maintain all the existing equipment that you have here in the Kingdom of Saudi Arabia. So going on from that, just to talk about some of the changes that have happened with the specifications, and there's three real areas here. One deals with the cold temperature area, one deals with the intermediate temperature and the fatigue cracking or other types of cracking area, and one deals with the high temperature rutting type performance. In the cold temperature cracking, What we have is a piece of software that we developed called ZAR, which does a critical cracking temperature analysis. And what this piece of software does is it really shows the importance of rheology in trying to look at the performance of the asphalt binder, and it does make the use of fracture tests. So it combines the use of a fracture test with the rheology coming out of a bending beam rheometer. What I should say here is that the rheology that's defined by the bending beam rheometer, even though you have a warmer temperature, a warmer climate here, is actually very important to you. It actually defines the stiffness in a high temperature, in a high stiffness range very accurately. And even in a climate such as Saudi Arabia here, the importance of the rheology in the high stiffness end of the spectrum is still important for how your materials behave in terms of cracking performance. So in the US we have this cold temperature cracking, but the rheology is still important. I'm going to show a little bit more about this in a minute. In the intermediate temperature, we have this sharp fatigue parameter, which was developed based upon dissipated strain energy. G star times sine delta is related to the dissipated strain energy. And this is what I did my PhD work on. This was initially the parameter that we adopted for the intermediate temperature. It does a reasonable job. The other parameter that's being looked at now is this parameter called the Glover-Rowe parameter. Somebody gave this name to the parameter. I'm the Rowe part of the name there, and Charles Glover, who's a researcher down at Texas A&M University, is the Glover part of that parameter. And some work done by Mike Anderson, Gail King, and a few other folks noted that parameter was related to durability cracking on airfields. It's also very important for things like recycled asphalt pavement. And that parameter is basically the modulus. So you have the G star modulus. Andrew, I'm doing something wrong here. I have a switch. Right, so we have a G star and a phase angle, and these things are very simply computed using that little equation there. High temperature, we're using the multi-stress creep and recovery test, and I'm going to just show you what that is as well. This test was developed by a gentleman by the name of Mr. John D'Angelo, but since he's been developing this test, he became Dr. John D'Angelo, because in developing this test, he completed his PhD at the University of Calgary. So he did this test as part of his PhD development work. So bending beam rheometer, what we have is a very slender beam. This is a picture of the apparatus. I know you have this apparatus in your laboratory here. And what it does is it very nicely defines the stiffness in a high temperature region. We actually collect the stiffness for 8 seconds, 15, 30, 60, 120, and 240 seconds. Normally speaking, we only use that 60-second information and we throw the rest away. If you use that full information, you actually can define the rheology of the binder in a very good manner. So it's actually a very good rheometer, does a very nice job in defining the rheology in the high stiffness region. In terms of understanding the BBR data, what we should note is that the BBR and the DSR, they're both rheometers, and we can take data from the BBR and convert it to the same format as the DSR data. So we can take the S and the M that we get from the BBR, and we can convert that to a G star and a phase angle, or vice versa. This is called interconversions. So the stiffness at 300 megapascals is basically the same as a G star at 111 megapascals. The 0.3 M value that we use is the same as a phase angle of 26.2 degrees. This is the original calibration of the low temperature cracking. These were the points that failed, these were the points that were okay. And if I want to put that, I can put that as this was the no cracking, this was where they have cracking. You see, I also have G star on here, and I also put phase angle on that graph as well. So we can relate those two devices very well. So if I want to, I can obtain the dynamic properties at the high stiffness region from the bending beam rheometer, and I can combine that data with my analysis of dynamic shear rheometer data. It's a very powerful rheometer in getting information. For the cold temperature binder specification, we did this type of analysis. This is our ZAR software, which is developed by my company, Abatec, and we take the data from the bending beam rheometer and we calculate the thermal stress. This bottom line here is the thermal stress, and as the pavement cools, it wants to shrink and contract. And as it builds strength, eventually it gets to a point, this second line here is the strength, it gets to a point where all of a sudden it goes bang, and literally the pavement will fail, and you'll hear, if you're standing next to that pavement when it fails, you'll hear the sound bang as it fails. You get this large crack going on. And one of my old friends in asphalt technology, a guy called Ken Candell, was actually telling me that one time he was standing next to the road, he had just done an inspection of the road surface, and he had got no cracks over here. He turned around, was writing something down, and all of a sudden he heard this large noise, big bang going on, and he turned around and all of a sudden there was a crack in the pavement where that material had just fractured. So, this will really give you an acoustic event. There's a standard specification for that. As I say, that low temperature thermal cracking is probably of less interest to you here, but the rheology that you get from a bending beam rheometer is probably important for your for your cracking behavior. Okay, I'll explain a bit more about that in a minute. This is what we call the level row parameter. In the intermediate temperature, we have this existing superpave parameter, D star sine delta, and this gives us information related to fatigue. And this really is dependent upon the rheology of the binder in the range of low to intermediate. So you go from low temperature to intermediate temperature. This G star times sine delta, it really ensures that rheology is correct in that range. This other parameter, G star cosine squared divided by sine, makes sure that you do not get excessive cracking. Let me just... showing the parameter. Asian value. I have binder types being shown. Low and binder was modified binder. Red, yellow, both modified binders. Modified binders from Asian. Not crack. And red, crack. Crack. Damage zone has the material crack. There's been several cycled asphalt pavement parameter that they could find that correctly of cycled asphalt. So parameter developed to on-load associated cracking. So this is something that's ongoing in the US at the moment. It's being looked at a lot. Stiffness really dominates our specification. What I show here is some different lines of typical binders. We have temperature on the horizontal axis and a stiffness modulus on the vertical axis. Here the stiffness modulus I put is G star. The low temperature cracking criteria is shown here. The high temperature criteria for rutting is shown here. If you take a binder like this green binder here, it have a certain performance window. Okay? Now you can go and modify that binder, and the blue might be one of the modifications of that binder, and you can increase the performance window by modification. But you have to be very careful about how you modify, because you need to make sure that when you modify, you understand fully the low temperature properties and the high temperature properties to make sure that you're modifying in the right way. If you just add a material that is going to harden the binder, you might end up modifying it and sacrificing low temperature performance. So you need to use a good modifier that has the correct balance of properties. In terms of high temperature, the high temperature performance in the sharp specifications that were developed originally around G star divided by sine delta. This was the original validation that was done. I was involved in the original validation. However, what we've noted in the US, as we've used more and more modified binders, this has not worked well. So we've now extended this to include the multi-stress creep and recovery. This multi-stress creep and recovery defines this parameter, which is called a non-recoverable creep compliance. We use the symbol JNR. JNR really is a stress-dependent viscosity. You know, sometimes in engineering we put these complicated words there, non-recoverable creep compliance. It sounds complicated, it sounds like a complicated word, but really it's just a viscosity, okay? What we're doing here is we're capturing something which is viscosity. It's trying to get something that's behaving closer to a viscoelastic solid material compared to a viscoelastic liquid. All binders that you get from an asphalt refinery, bitumen, just regular bitumen, whether it's blown, whether it's oxidized, whether it's a pitch bitumen, they will be a viscoelastic liquid. It'll be a viscoelastic liquid if they're at minus 30 degrees. It'll be a viscoelastic liquid if they're plus 100 degrees. Okay? It's not until you start to put some chemistry in that, with polymer modification, cross-linking, that you start to convert that material to behave closer to a viscoelastic solid. Okay? So it's very important just to remember that all these binders are viscoelastic liquids. Now, in terms of a viscoelastic liquid, what we mean is if we look at this shows a graph. If I load a binder, take the load off, I get some elastic deformation, I then get some viscous deformation, take the load off, I get a bit of elastic recovery. Here I get permanent viscous strain. So here, this is a viscoelastic liquid. A very simple model. Model this with a simple one-element Maxwell model. Typical binders are a bit more complicated. You see here I've got an elastic response, viscoelastic creep, elastic recovery, viscoelastic recovery. I've still got permanent strain. It's still a viscoelastic liquid. And most of our binders will sort of behave a bit like this. Now, if I get a viscoelastic solid, what I enable this to do is come back down to zero. If it's a viscoelastic solid, that will come to zero. And that's what I would ideally like. I would like my binders to come close to a viscoelastic solid. So we have this test, MSCR, which is performed in a dynamic shear rheometer. This is showing the test configuration. Here I show you have a sample in a rheometer. Here's a little sample of a binder. During the test, we start at this point A. The rheometer to a point B, and we put a load on to the rheometer, take the load off, comes back to a point. What's happening? Here's the load going on at point A, up to point B, you take the load off, covers point C. Going on in a test. Here you have your recovered strain, here you have your unrecovered strain. ANR, this strain, the unrecovered strain, divided by the stress. So compliance, we strain divided by stress, whereas in modulus, stress divided by strain. We can also calculate the amount of recovery, recovered strain divided by the stress as a percentage. Now here you see results for two binders. This green binder, red binder, structure. What we have here, tests conducted at different levels of stress. Now, standard MSCR test, we use stress levels. 100, 1,200 pascals. 100 is here. 100 pascals is a very low level of stress. It's basically in the linear region. So it's a low level of stress, not too similar to the level of stress that you would use in that original sharp specification, measure the G star divided by sine delta. This higher level of stress is significantly higher. You're going very much into a non-linear region of stress. And what you're doing here is you're saying to that binder, look, sample of asphalt binder or bitumen, are you strong at this test, stress level? Down here, okay, yes, I'm nice and strong. Now you take it to another stress level, I still have that same strength. This binder has lost its strength. Binder is still strong. But what we're trying to say is we need a binder that's going to be strong over a full range of stress levels. You can understand. You know, you can imagine that binder supporting the load. In some cases it can support it well, in extreme cases. In some cases. So Ron, when he was doing his research work, did a whole bunch of different stress levels, and to make a specification test you normally have to have some sort of compromise. The compromise was that this 3,200 stress level was reasonably close to what would be expected in the pavement asphalt binder film to undergo, reasonably good at distinguishing between the different material types. So this is what went into the stress level. One which gives us a very similar number, performance we would get with the old specification, and one which would really enable us to distinguish between the good performing binders and the poor performing binders. Here I show an example of, I have two different types of materials. This one on my next slide, types of materials. This shows the results of a 6422, this conventional unmodified binder tested at 70 degrees. And here you can see stress of 100 pascals, here 3,200. You see the little load going on. When I put a load on, there's no recovery. I get strain, no recovery, strain and no recovery, strain and no recovery, and so on. And at the higher stress level, you can step look as the strain goes on. Replicates that way. Each of those sort of lines is three lines on top of each other. Look at the total magnitude. Number here, 200. Okay? For that number 200, at test, I have 200 plain units for that particular binder. Okay? This is a standard asphalt paving grade PG64 material. Now I put this one on. Okay? Look at the difference in the shape of those curves. Now I put the load on, that material bounces back. I put the load on it, it stretches and bounces back. Stretches and bounces back. So these are the load pulses going on. They look actually more like load pulses, but load pulse. Here's my permanent station. What was the number I had before? 200, yeah? What's my number now? 0.05 maybe? Okay, it's like virtually nothing. If I had that on the same scale, that would all be crammed down right at the bottom. Okay? So really here I've got something which is behaving very close to a viscoelastic solid. Same binder, same PG6422 binder, I'm using a lot of polymer with it. So this is showing what you can do with modification. It also shows how that test can distinguish very nicely between the polymer modified binders and the conventional test. So, you know, I congratulate John D'Angelo for doing such a great job in developing the test. It is a real improvement, and I would definitely recommend the Kingdom of Saudi Arabia to adopt this test, particularly because of your high temperatures in evaluating polymer modified binders. The types of specifications that we have in the US, we use 64 standard, 64 heavy, 64 very heavy, 3. Those will have A&R. And then we'll have PG grade 70 with the same letters, grades 58 with the same. In the old system of the superpave specification, the first system, we use something called grade bumping. Okay? Now, I live, you know, in the New Jersey, New York, Philadelphia metropolitan area. Okay? In that area, our pavements are in a PG grade area, 64 degrees area. That means our pavements get close to 64 degrees C in terms of their high temperature performance. Now, on the tollway, you know, the heavy traffic routes, toll booths, those heavy areas, they would typically use not 64, not 70, they would typically use maybe a 76. They would do what they're called maybe 1 or 2 grade bumps. So they would bump the grade from 64 to 76 to account for slow-moving traffic, heavy-moving. Now in this system, you don't do that. You use the standard for your regular roads, and then you do your grade bumping by going to heavy or very heavy or an extreme type specification. So it's more in line with the original superpave and sharp specifications, that you're evaluating a property at the temperature that your road is. This is much more consistent of superpave rather than the ad hoc grade bumping that was adopted in the mid-1990s. So this is a slightly different approach. AASHTO specifications for these are all standard, they're all published, and you can get hold of these fairly easily. Now the importance of rheology and this thing called the R value. The original specification table, there's a report that I can give you a link to up here with some of the history of the element. In fact, maybe I will put it on one of the sticks or the with our sponsors here, we make sure you have a copy of this. The original report. And the concept was that you have a logical index to... Now, specification that got implemented, because we have both BBR and DBR on the same aging condition, both on PA, we have the rheological index effectively by default. Rheological index, the complex modulus frequency, master curve, and I'll show you that in some other graphs. Look at complex modulus frequency or complex modulus plotted against phase angle. Related to speed cracking, related to something called the relaxation spectrum of the binder. It's very important for controlling cracking. This shows binders. It's really the same plot as this, but I've got here 3 different values of rheological index. I've got frequency, I've got modulus. The rheological index of a 1.1, 1.7, 2.5. 1.1 is a 10, 64 minus 10. And you can see how the shapes change. And this data plotting G star versus phase angle. Same data. What we know here is that
versus face. The data in a face, all of a sudden it becomes very important for determining where that cracking will occur. Remember earlier on I showed you the plot of the Glover row parameter? The Glover row parameter showed a line in this black space. As the materials age, they start to cross that line. Where you are in the black space, it's very important how your materials have something which is prone to cracking, prone to cracking. The other thing is to note is that this rheological index, R value, is also related to the chemical composition. So depending on the refinery you use, the oil wells, type of oil going into that bitumen will affect performance like this. Also, as that material oxidizes and ages, it will change stuff like this. As you oxidize materials, make more asphaltene, some of the resins and saturate materials, as they oxidize, they tend to more asphaltene parts of the bitumen. This is what we see that occurs when we age. Aging, the R value, rheological increases, crossover reduces. So you basically change the shape of the binder of the plastic. Here I show some tours from Newark. Newark Airport is the airport I fly out of to come here. New York City. This shows some tours taken from. This was that 6422 material, not cracked. These were polymer modified materials. These were the materials that they thought they were applying extra quality with. For more aging. When we plotted these using the Glover row parameter, they crossed that line back in the row parameter. The other thing I'll add here, aging is going in this direction. If you use the graph on questions or discussion we had yesterday, and the possibilities of graph in the behavior, aging goes like this. You want to reduce all your properties, asphalt binder, rheology, opposite way. Goes one direction, any rejuvenation you do in the other direction. So we have tools that we're developing to help us better understand how these materials change their properties, they age, how they crack, and this is all very new. This type of work is really being done in the last 3 to 4 years in the US. Okay? So it's brand new. The linkage that you have with us all here, we will make sure that you keep fully abreast of these developments as they occur. I mentioned earlier that the chemistry is absolutely tied to the rheology. And this shows some old data going back to 1992. This is a paper a colleague of mine, Dave Anderson, published, and it shows how the R value here, this is what was measured, thermometer, what's calculated, chemistry. Here's a few equations, asphaltene, saturate, all aromatics, clean aromatic fractions within a bitumen, and the molecular weight. That was of that sample. You can see here the equation for the shape of the master curve. Here I have my asphaltenes, saturates, polar, and my naphthenic aromatics. Then I have my molecular R value. Calculate all the other parameters using different equations. We can link the chemistry and the rheology very nicely together. The other thing I'll mention, this was done in 1992. We have lots more data. I just put this one on because I had a nice simple graph to show you. These were all the sharp core asphalts. Have a lot more data since that time, and a lot more work has been done, types of analysis. We can get a lot of information from things like FTIR. And I saw in your lab here that you have FTIR. There's lots of information you can obtain in terms of analysis of data to to get very good information on the rheology. So when I think of the binder critical design parameters, thermal cracking, BBR, test and cracking temperature, what we're using in what we're recommending is people who have major cold temperature issues, probably. What I will say is BBR for you is still very important because BBR is helping you define the rheology in that area where the binder is more sensitive to cracking. Thermal fatigue and durability cracking, low parameter G star, this should be a because of the phase angle score divided by the we have rutting, multi-stress creep recovery test is the best for rutting, and then you have to affability saturation test. What we want to do is we want to achieve binder good spread of rheological properties. That binder to be able to relax stress as well, and we want that binder to be strong to resist deformation. You can do work with chemical analysis, things like the SERA analysis. SERA is really an automatic Coulbet analysis. Put your binder into asphaltic resins, your saturates and your naphthenic aromatics. You can get initial estimation of the properties of that analysis. Ideally, you want a soft base with a range bar value. Modification of the binder can increase that stiffness at the high temperature end very well. In terms of the mix design and what we're doing with the mixtures, we have the superphase mix design procedure developed around about 92, 93. That's been published with a directory. Since that time, we've been teaching, I teach a course with a gentleman called Jerry Huber and Bill Pine, and a course that deals with a more detailed evaluation of the VMA and finding the mixtures like VMA and air voids. The Bailey method is a way to define full straight method. We do a 1-week training course method. We did the last one I did was up in the Calgary, Alberta, Calgary and so area that we could bring to the and we could involved in teaching this. It's not complicated, it's very detailed. And when I say it's not complicated, I don't mean that you have to solve these equations or a PhD in mathematics. It's very detailed in the fact that we have lots of follow to understand how your aggregate structure is behaving. So it's something that would be very good for your conditions. Mixture test, there's a whole series of mixture tests. In terms of what came out, the simple test, some folks are still using this. Every now and then we get asked to help somebody from what was made about 20, 30 years ago, working. So we can do that for high temperature climates. Other important tests, bending beam devices, and then tracking is also important. Things like the overlay test. Overlay test is very important for rack mix. Then there's a few other options that exist. The indirect tensile test, which was developed by Ray Root for the evaluation of mixtures. What I thought I'd do now is I just invite Andrew Cooper just to come back and just talk about these bits of equipment. But I'll let Andrew just go through some of that.
Hello again. I just wanted to say a little bit about Hamburg wheel trackers. Wheel trackers are, Hamburg wheel tracker is more and more important around the world right now, but even before the Hamburg wheel tracker, Cooper wheel trackers probably 1990. I guess that my father was trackers and designing them for the University of Nottingham. Before that, maybe in the 80s, maybe 70s trackers. Personally, I know that wheel tracker, my first wheel tracker design is still being used at the University of Nottingham every week. So we've sold more wheel trackers in the world than any other company. Here we see two machines that we've with James Cox and Son. Devices here have been made in California. At the moment in the United States, Hamburg wheel tracking is a very, very popular test method being adopted by that way. On the right here is developed specifically for Caltrans, Californian Department of Transport. And what they wanted and what they couldn't find anywhere else in the stainless steel. There were machines that looked like they were stainless steel, but magnet against them, magnet looked thick. It wasn't proper stainless steel. Now in California, the only machine California Department of Transport will purchase stainless steel, and also we've worked very hard with them to produce a way of interpreting slope and the stripping slope. That's that all-important selection. We're the only people automated way of analysing the data that by the test and telling you whether you have a stripping inflection point, whether the material never reached that stripping point at all. This is we saw downstairs in the labs. This is the ASHTO configuration that you get when you're Hamburg wheel tracking. Examples that your gyratory factor with a fine cut across. And in the States, they perform asphalt mixture performed on specimens that gyratory compactor. However, I wanted to show this, and this was yesterday. Outside of the US, often prefer production of samples for wheel tracking. This type of square configuration, either 305 square or 320 by 260 millimeters. And how this is compacted, or compactor, vast majority of the cases. So, then this is sold in huge, sold them down into Australia, Argentina, Canada, Russia, all over the world by these devices is because that surface there is based upon the diameter of a road roller. What it produces something that the most closely relates to what occurs out in the road, because we're mimicking the effects that we roller. And we compact here directly into the mould. So we put our mould in, our roller comes down, compacts until we reach our specified void content, our specified density. Then we take this out again and we can put it directly into our Hamburg wheel tracker, or our dry wheel tracker. Very, very popular method of making specimens for wheel trackers. And additionally, testing as well. I don't think at the moment this is such a popular test within the Kingdom of Saudi Arabia. Certainly elsewhere around the world, whether it be China, Australia, all the way through the Americas and in Europe, 4-point bending is a very, very popular way of assessing fatigue. In Europe, we have a European standard, and I'm part of the committee tasked with developing the standard and revising it. In the US, there are standards for ASTM and the AASHTO standard. Jeff Rowe here is involved at this present moment in time in revising those standards. Again, we've sold great numbers of, probably also we've sold more of these than anyone else in the world. If you look at this device, which is by Cooper, this device which is to the AASHTO specification by James Cox and Sons. One of the things about a fatigue test, a 4-point bending fatigue test, it takes quite a long time to perform. So now in the US, go along with your Hamburg wheel tracking from the deep water sensor. They want cracking tests. They want quick cracking tests that will assess this material is cracked when it's in the road. So we cracking. Here I've shown the popular tests in the US at the moment. Have the semicircular bending test, which has a provisional AASHTO specification and is being used balance mix design method down. This shape compact tension, which is used more frequently for low temperature cracking, and was designed by Bill Butler, Professor Bill Butler at the University of Illinois. And on the right, a test which has been around since the 1970s and was originally designed to investigate overlay, as you say, and reflection cracking with overlays on top of. Now, possibly the test will go forward to be the most popular of all the three of them there, and will be used in this balance mix design method. So it seems from every time we go to conferences nowadays, a lot of involvement, a lot of interest in this. We're now going to be working with the Texas Department of Transport, TxDOT, on developing this design, and what we hope and believe will be again the best piece of equipment performing this test. And with that, I'll pass back to Jeffrey.
So I just really want to make a couple of comments about designing for extreme climates. Here in Saudi Arabia, you have somewhat higher temperatures than what I'm used to back at home. Back at home, I have nice snowy winters, and we actually have a different range of temperatures. Here you have extreme high temperatures. So I know you have some provisional, or I'm not quite certain how provisional they are, PG binder zones, but the important thing about selecting your PG binder grades is that the climate zones provide the basis for that selection. And then built into that, we do an analysis with the traffic loading that would occur in a particular region. So generally, there's fairly excellent climatic records around, and I'm certain in the kingdom here you have excellent climatic records. So to go and do an analysis of pavement effects is fairly easy. What we do is where's the point on What we do is we have again some finite element software or that we've developed, the average and might be the size a pavement structure temperatures in no analysis of like the analysis highways here. But one thing that you do know is that the old method that was originally specified
1994 was changed in the 2000s. Around about 2004, 2005, changed the algorithm. So just bear that in mind. We can help you with that if that's something you're interested in looking at. Okay, in terms of the specification grades, the way we need to we would recommend that you adopt some sort of aging durability parameter, something like the Glover-Rowe parameter, something like the MSCR to define the high temperature, physiology of the define the cracking, supplement some sort of fracturing. In terms of mixtures, tests that Andrew were talking about, the semicircular bend test, the direct compact tension test, or the Texas overlay test, approaches to go with. In terms of binder, what I'm looking at the moment is like the Wheelet pendulum cohesion tester. This is another test device that Cooper manufacture and sell. Something that's been adopted fairly extensively in Europe for looking at the quality of binders. Has a good temperature range, good cohesion strength. Here, and again, we could provide you more notes on that. I had a paper conference in high volume roads. You know, you could use something like the simple shear test. The Hamburg provides a much easier way of going and analysis to data you get. On and either wet, dry, look at moisture damage, or you can do dry tests to look at just the effects of cutting and binder viscosity. The other thing I'll say is you can do that test at different stress levels, different load levels. In the US and in Europe, there's standard load levels being used, but that doesn't mean that test can't be developed to do an investigation of load levels. I'm certain that's a fairly Superplave, by the way, for the wheel tracking evaluation, we looked at 2 stress levels. At 550, I think is about the old standard in the UK. Yeah. If I remember correctly, about 800. If I remember, that was the high stress level we looked at. So we looked at the average stress level and the high stress level. And I think the UK standard now is somewhere in between. 710, and that's newtons. So there are different things you can do with that. Mixture of important to understand, and we're doing a lot more analysis these days. I mentioned that Bailey method for wheelie, which is advanced superpave method of mixing line, and we'd be very happy to work with you involved in the roads in the kingdom, sort of implement some of that technology as well. Aggregate packing, design of the mixes. So, in terms of a summary on what we've talked about today, this sort of summarizes where we're at. Left-hand side is binder, right-hand side here deals with mixture. On the binder side, you know, the chemistry initial of the potential for that binder quality. Binder evaluation of the laboratory, PBR and DSR. Do a lot of stuff with PBR. Some folks want this bit maybe being replaced eventually, but temperature parameter, other row parameter, and the other superpave parameter. High temperature, use the multi-stress creep recovery test. Aging, you have both RT understand the binary. This pretty much summarizes those tests. Improvements to designs with consideration of volumetric design. SuperPave and SuperPave Plus daily method, understanding the volumetric spec, like IDT. Recommend Hamburg wheel tracking test, quality control. Until we can do climate data and make some grade selections. Other factors like traffic, reliability. And what we do, as Abatec and Cooper, with our partners, we can offer a lot more analysis, have lots of tools, very sophisticated software tools for analyzing binder. We have some of the best software in the world. We work with most major rheology analysis software. Is in use in pretty much every continent. There's hundreds of copies out there being. So that's sort of a summary of the types of technology we offer. I wanted to invite Tony just to say a couple of concluding comments to wind up the presentation.
Gentlemen, my name is Tony O'Brien, Irishman, bit of a wanderer. I was over here last September, October, and I think it finished up around Christmas, and these gentlemen approached me and said that there was a very good market here for material testing equipment, and if I could source good supply for such equipment, there was a ready-made market here. During my research, I found a company, Coopers, and I met with Andrew, with Peter in London, and we discussed it. And Peter outlined that they had some agents working in the Middle East, but they didn't have a very good professional setup here. I went back to the people yesterday, then we discussed it. And I said, for it to be a success, we needed to work with a company who are willing to put their hand in their pocket, put in a proper structure, and then it could go forward. Then they told me that they had met with Fahd al-Sahly, and that he was willing to invest in, over the last, going back to Coopers, obvious, as you can see from their global presence, that they are operating in many countries all over the world. Peter outlined to us yesterday that they are sending equipment to Australia over the last number of years. Going back, met with the people, and they said that Fahd al-Sahly was willing to stock equipment, willing to invest in spare parts and service, willing to invest in office and showroom, and above all, he was willing to invest in top personnel and bring them from overseas. And as you can see over the last 4 months, and I think you can now see, showroom has been built here in then we discussed about how we get into the market and how we get to know. And said we would have this seminar. And then and we would invite MOT, universities and contractors. And we received a commitment from Andrew, from Peter, and from Professor Jeffrey. And I must say, over the last few days, together we've built up a very good partnership and worthwhile relationship. We often hear about teams going away for bonding sessions. Can you imagine English fellows and Irish and that, and bonding in Riyadh without a beer? But we achieved it. Yesterday we had a meeting in the MOT, And I must say this was, I suppose, a highlight in various ways. Mainly because not alone was it an opportunity where you can sell your wares, but it gave us a great insight into the progress, and I don't think even the lads here realised how far advanced Saudi Arabia is to the quality of their testing material and their insight into the whole road building structure. And I think it has developed for us a cooperation that when we finished last night at a meeting, the lad spoke about multi-entry visa, residence. When you get that, it will just put into your mind that their commitment is not for this weekend or for today and tomorrow. It's a long-term commitment. And I would reiterate that, and I would say to the contractors here that it's a commitment to you also, by the Al-Sahly and their partners. And you have our cards, you have email addresses. Just because you might need something, if you have an idea that can help in and benefit any of the here, I think everybody can benefit from. Again, I would like to give my assurance that this will be a commitment and the partnership will follow on. I would also like to say that with Fahd Al-Sahly, we have developed an equipment selling dealership where we will be selling lama, asphalt plants, care, concrete plants, and beltwaying systems and crushing systems. But again, it's an ongoing process and will take a lot more time and a lot more effort. Finally, I would like to thank the gentlemen here today for coming here, for the commitment they have given us. There was times last week when we didn't think Jeffrey would make it here because visas and other problems. But in general, it was a success, and I am delighted that they made it here. I would like to thank each and every one of you for coming here. And I think, as I said, not the last you'll see of us, and hopefully the last we'll see of ye either. That I think it's something that can be ongoing, and we can try to have another seminar maybe later on this year. And he's not here at the moment, but I must say a big word of thanks to Fahd Al-Sahly. Because above all, and I've met a lot of people here over the last few years that I've been here, but he has been one person that will do what he will say what he will do, and put his money where his money. And the showroom is open, the offices are there, service personnel are on the way, and I hope, and I'm sure, it will be a tremendous success for Coopers, for Jeffrey, for ourselves, and in general for the people and for the infrastructure of Saudi Arabia. And I think everybody will benefit from it. And again, if that's what I have to say today. If there is any questions, I think the lads are free and easy to work with you and debate. May not be a question, it might be a point of view. It will be well accepted. In Irish words, Rabbil Mahagwif.
Thanks, Tony. No, I just would like to say my thanks for all of you for listening. I don't know if you've got any questions or discussion for me, myself, or Andrew or Peter. Yes, sir. In terms of the volumetric design, you might have some issues with the volumetric procedure. And to be honest, we can look at some of this. If you can share with us your mixed designs, I can put some of this into the Bailey method and to try to understand some of what's going on there. We might find that certain designs can be more sensitive and certain designs can be less sensitive to compaction variation. And I can just put very quickly and go back on some of these. This graph here, in terms of how we see compaction sensitivity of mixes. We have mixes over on this side of the curve, a lot less sensitive to compaction. Mixes on this side can be more sensitive to compaction. We can understand the sensitivity to compaction by some better understanding and some better tools of trying to look at these mixtures. The other thing that we might suggest that you want to do is to look at a statistically based percent within limits type specification. Most of the DOTs in the States these days are going out on a statistical specification. And I think here you're just using ranges, as I would anticipate. Yeah. So there's a few things we could do, and maybe we could, communicate some of this by email. But there's certainly some things that might help us understand. Without looking at your aggregates and without trying to understand, it's a little bit difficult. There's some tests we can do to the aggregate that could understand things like crushing potential, how those aggregates are packing together, how they might consolidate under traffic. The other thing is that, you're using the end design of 100 gyrations. Maybe that end design should be 125, maybe it should be 110. Maybe it should be a little bit higher to represent your field conditions more closely. So those sorts of things need to be considered in terms of trying to understand your situation. But I mean, it's an important point, and at the end of the day, I had the pleasure of working with a gentleman who's no longer with us now. His name was John Edwards, and he would just always stress to me the importance of the volumetrics, the asphalt absorption, the need to do good calculations, and good mixed design practice. So, I'd be very happy to work with you, very happy to look at some of your data, if we can do that. Thank you. Yeah, Pete, do you want to address the plans that you have with Malvern and Bolin and?
In answer to maintenance for the machines, as people have expressed concern to us while we've been over in the Kingdom Saudi for the last few days in terms of maintenance and support, where we have done well around the world, we have in place partners that can maintain equipment for our customers. So we plan to put in place a training program for our sahly engineers to be fully trained and conversant with all of our equipment, not just for maintenance, but also, as I mentioned earlier on, calibration. You make significant capital investment when you purchase equipment to test the properties of the material. It's important then that those results that equipment gives are accurate and reliable. We know that, we understand that, and we spend a lot of time communicating that with our partners. We've had a fantastic commitment from Al Sahly in respect to engineers spending time in the UK, learning about equipment, learning how to calibrate the equipment, spending time in our workshop where the equipment is built so they understand the fundamentals of the equipment. The other thing that we spoke about and we've heard about is relationships with such as Malvern and a poor support from Malvern. I was speaking last night to Tony and Mr. Fahad, about having backup units in our showroom. The DSR is a small machine. There's no reason at all why we cannot stock a machine. So if your machine goes down and it needs repairing, straight away we send out a replacement machine. So in terms of operation, you're up and running immediately. We then repair that machine, and if it takes a long time to repair that machine for parts waiting to come or any other reason, you don't see that negativity of the machine not working. As soon as your machine breaks, we send out a replacement machine and you're up and you're operable. We repair your machine. Once we're up, we're happy, the results that are coming back from your machine are good and the problem's definitely fixed, then we exchange back. We think that by offering this type of service, we can offer over and above anything that you've been offered before. And again, as Tony said, Mr. Fahad's investment in having capital equipment in the showroom will help tremendously. We were talking last night about spare parts and consumables. There's going to be parts and consumables held here in Sahly. When we talk about that, I talk about our factory in UK. We've had to take on a third factory in UK purely for stocking of parts. We've been putting this equipment out now for 25 years, and we understand how important it is that your equipment is operable all day, every day. And the only way that we can ensure that we've got the parts is by holding them in stock. So we've invested heavily in UK in a third factory that's full of parts, but for equipment that we live in a real world. Machines break. If some of our equipment, and James Cox's equipment is there and it's been there 20 years, but parts break, they wear out. But we've got a good vast array of stock in UK, and some of that stock's going to be held here in Saudi. And the engineers will come to the UK, they'll build the machines, they'll build brand new machines, they'll be trained fully, they'll get the certificates of competence, they'll understand calibration, and I think we'll be in a position to support you better. Just one last thing on that. What works well for us with lots of customers also around the world is that when they buy a machine, they buy a service contract. So that you pay a few percent more when you buy your machine. But what that ensures is that there's an engineer that's on hand. We guarantee 24-hour response time. Because you've took out the service contract, you get priority service. So if you pay for the service contract, an engineer comes out twice a year to service your machine, oil, grease, and maintain, and once a year he'll calibrate the machine. That way then you know that you've got no unexpected high invoices coming your way for repairs. You've paid it at the beginning of the year, you're not going to get no unexpected invoices, and you get priority service. And the customers that have got those contracts in place have given me nothing but excellent references over the years, and that's enabled that service and support system that we offer to expand massively. It's a very important, well-raised point, the service and the support of the equipment. Very, very important.
Do we have any more comments or questions or discussion? Yes, sir. I'm sorry, I didn't quite catch. Does this bring us to a close? Well, I think we're getting very close to the time that we should be finishing, and I would like to just again offer my thanks to all of you for attending. Pete, Andrew, myself, and I'll show cards on the table at the end. Please feel free to communicate with us. I always like to think of all of you as my friends and colleagues in the industry. I'm really happy to meet all of you here. We're very happy and feel privileged to be here in the Kingdom. Thank you very much for taking time and joining us today. And, you know, if you want to correspond, I will try and get you files and papers and information, anything you ask for, which I can help you with. Very happy to help and work with you. Tony, do you want to say any final? Thank you very much, everyone. Thank you.
Yeah. Every time, right?